Hello, ladies and gentlemen. Tonight we are going to talk about the fundamental parts of a function. So some key terms are function, input, domain, output, range, discrete function, and continuous function. So let's first talk about a function. A function f of a variable x is a rule that assigns to each number x in the function's domain a single number f of x, the function's range. The word single in this definition is very important. So I can have, sorry, pen. So I can have the numbers 1, 2, 3, 4. And let's say I also have the numbers 8, 2, 5, and 9. Now let's say that the function takes 4 to 5, 3 to 8, 1 to 9, 2 to 5. That's a function. Every number has one unique path that it follows. Despite the number that it ends at, there's only one number that it goes to. Now, what's not a function is if I have 1, 2, 3, 4, and 8, 2, 5, 9. Now, let's say this time 1 still goes to 9, 2 goes to 8, but then 2 also goes to 5, 3 goes to 2, and then 4 goes to 9. This 2, because it takes the 2 paths to 8 and to 5, makes it not a function. So this is a function. This is not. So a function, there's the definition again. Let's check to see if we could find out of here which ones are functions and which ones are not. So 1 to 25, negative 5 to 13, 0 to 10, 125, 2 to negative 13. Every variable here has its own unique number. Now, 1 pops up here twice, but where does it go? It goes to 25 each time. It's the same number. So it still is assigned to that one unique number. Now here we have negative 2, negative 3, 1, negative 1.5, 0, 0, 1, 1.5, and 2, negative 3. Now, we see that the number 1 here pops up twice again. However, what do we notice? This time it goes to a positive 1.5 as well as a negative 1.5. Again, one number from x cannot have two y values, so this is not a function. And let's look at this one. Negative 1 to 5, 4 to 5, negative 5 to 5, 5 to 5, and 10 to 5. Now, it says that each number x is assigned a single number f of x in the domain's range, in the function's range. So yes, they all go to 5. However, it doesn't say anything that the range can only have one x assigned to it. So yes, this is still a function. Yes. All right. So let's look at a function on the graph. So a function on a graph, and to tell whether or not it is a function, well, we have what we call the vertical line test. The vertical line test states that if you can pass a vertical line through the graph with it only crossing the graph once, then it is a function. So let's look at this one. If I come here, I cross there. Yes, it only crosses once there. Come here, it crosses once there. Come here, it still crosses once. It crosses only once anywhere on that graph. Now if I come to this graph, it crosses it here. It crosses at 1 point and 2 points. So right there off the back, we can see that, let's say 8 right here. It has two values, right? So this is not a function. It did not pass the vertical line test. Did not. That's line, not lime, test. All right. So check out these functions. Take a minute to see if you think these are functions. Now, Come on. I keep forgetting to select the pin. First time doing this. I'm going to pin. All right. So if I come here to this function, vertical line, it passes there. That wasn't very vertical. Vertical line, it passes there. Now if I come right here, let me see if I can do this. We could see that that vertical line runs exactly the same as this. So basically this black line here is a vertical line. Well, if we look at the 4 here, 4 has a value starting at about 1.5, and it has values all the way down to about 8. So this is not a function. This is not past the vertical line test. And we could see here that if we were to do vertical line on this one, it'd pass anywhere we do it. Now here, at this one point, it's tricky, but it should really only, if you zoom really far in, it would only cross right at that one point, and so on and so forth. This is, yes, a function. All right, input and domain. The number being input into the function, right? So you have a function, you have to put something into it in order to get something out. This is typically the x variable. All possible values of the input is called the domain. Output and range, the number of value that comes from the function process. This is typically your f of x value or your y value. The set of all possible values for your input is called the range. So if I have one of those tables, just like my pen. So let's say if I have a table, and I have x and y, and say I have negative 1, 0, 1, and 2. And then I get 3, 3, 2, 1, and 0. Now, this is my input, my x, and what I get out is my y, my output. Now, my domain for this would be the values of negative 1, 0, 1, and 2. Those are all these numbers that I put in. And my range would be the values of 3, 2, 1, and 0. So let's look to see what the difference between a discrete and continuous function is. So a discrete function, data or a function, is discrete if there are only a finite number of values possible or if there is a space on a graph between two possible points. So let's look at some examples of discrete functions. So look at a math quiz, right? You have 5 questions. The number of correct answers on a student's quiz is an example of discrete data. The number of correct answers would have to be one of the following. You'd either have 0, 1, 2, 3, 4, or 5 correct answers. You cannot have 1.5 correct answers, so to speak. It is a discrete point. If I were to graph that, if I were to graph the possible outputs for the student, well, he either has 0 correct, 1 correct, 2 correct, 3 correct, 4 correct, or 5 correct. There is nothing that connects this to each other. It's one or the other. Same thing, apples at a grocery store. If you go to buy apples at a grocery store, you can only buy 1, 2, 3, 4, so on number of apples. You cannot buy 2.35 apples. Now, a continuous function. This is data or a function is continuous if there is no exact measurement for the data. This can be represented on a graph by a line or a curve or a partial line or curve on a graph. So continuous data is pretty much all other numerical data other than countable items. This is typically associated with some sort of physical measurement. So the height of a tree at a nursery, for example, is of continuous data. Is it possible for a tree to be let's say 60 inches? Yes. But it's also possible for that same tree to be 60.1 inches or 60.0023 inches, depending on how exact our measuring device is. So it is a continuous data. The growth of a tree is a continuous function. At any given point, that tree has grown. It growth is continuous, right? Now it might plateau off at a certain point. However, it still is continuous. A tree might grow really rapidly at first and then die off. However, during its entire growth, it does not stop. A tree does not start to grow and then stop here and then, all of a sudden it's that much taller. It does not just skip any length, right? It is a continuous length that it's growing, so therefore it is a continuous function. Let's look at some examples of discrete and continuous. 2x minus 1. So if I plug in negative 4 to this, so this is my discrete. I gotta remember I wish this pin stayed on all the time. Alright, so this will be my discrete side. So if I have f of negative 4, that equals 2 times negative 4 minus 1. 2 times negative 4 is negative 8, minus 8 is negative 9. F of negative 2 equals 2 times negative 2 minus 1 equals negative 4 minus 1 is negative 5. And then I have f of 0 equals 2 times 0 minus 1. 2 times 0 is 0, minus 1 is negative 1. Negative 1. F of 2 equals 2 times 2 minus 1. 2 times 2 is 4, minus 1 is 3. And then f of 4 equals 2 times 4 minus 1 equals 2 times 4 is 8, minus 1 is 7. Now, we can see that we got those numbers directly from here, right? These numbers right here are the same as these numbers right here. And when we go to plot this data, we'll say that this negative 2 and negative 4, negative 4, negative 2. And then we got 0, 2, 4. And we'll go ahead and label this 1, 2, 3, 4, 5, 6, 7. So it only goes with 7. So at negative 4, we're at negative 9. So we're like, well, we're down there somewhere. At negative 2, we're at negative 5. Negative 1, 2, 3, 4, 5. So at negative 2, we're at negative 5. At 0, we're at negative 1. That's negative 1 right here. At 2, we're at 3. And then at 4, we're at 7, way up here. So we could see with just this data set, we have very distinct countable points, do we not? So that is why that's discrete. Now our domain for this would be what? Well, we inputted negative 4, comma, negative 2, comma, 0, comma, 2, comma, 4. Now our range would be our outputs. So we have negative 9, negative 5, negative 1, 3, and 7. Negative 9, negative 5, 1, 3, and 7. Now on this part over here, let's say we're going to work with x is greater than or equal to negative 3. Well, if we're following along already, we can go down to negative 3. We're going to be way down here somewhere. So negative 2, negative 4, sorry, negative 3. So if I plug negative 3 in here, I got negative 6 minus 1 is negative 7. Right there. Now, we're going off of the function 2x minus 1. Now, we know the graph of this function already based off of these previous data points. However, we could say we're here. At 2, we're at 3. And at 4, we're all the way up here. So, however, when x is greater than negative 3,